As we continue our examination of soils and their water management, we turn our attention to water. The water in the soil is as important as the soil itself. This unit focuses on the relationship of soil, plants, and water. Particular emphasis is placed on the movement of water from the soil to the plant. Root growth and the viability of most soil organisms depends on there being a proper balance of air and water in the soil pores. If you recall the basic structure of soil, you will remember that pore spaces in the soil can be occupied by atmospheric gases or by water. In the natural functioning of ecosystems, water makes its way to these pore spaces, or is added to soil, by atmospheric precipitation, such as rain, snow, ice, fog, and dew. Soil water can be increased dramatically by flooding from lakes, rivers, or streams that have overrun their banks, or by a periodic rise in the groundwater table. In agricultural systems, we do not rely only on a natural supply of water to the soil, but instead we intervene by adding water via irrigation. Water availability in soils is an obvious necessity for plant growth and is a concern for agronomists, landscape managers, and gardeners worldwide. Irrigation has been practiced since the dawn of civilization in both the eastern and western hemispheres. In fact, some of the earliest laws ever enacted defined irrigation rights for farmers using waters from the Tigris and Euphrates rivers in what is now Iraq. Similar irrigation systems were used in ancient Egypt. Irrigation capability and technology advanced greatly in the 20th century. Many arid and semi-arid environments have been transformed into highly productive regions, but not without environmental consequences. These consequences will be examined in another unit. It is pretty obvious that crops need water for growth. But excess water can be as damaging as drought. Water-filled pore spaces in the soil exclude oxygen necessary for respiration of root tissues. Normal root function is reduced primarily because of reduction in available oxygen to the roots under flooding conditions. The low level of oxygen leads to a lack of metabolic energy in the roots that affects the uptake and translocation of water and nutrients. Also, root cell permeability to water can be decreased by this oxygen deficiency to the very incongruous point where plants will actually wilt while standing in water. The extent of flood damage to plants is dependent upon the duration of exposure and the stage of plant development when stress occurred. Obviously, soil water content is not static. It will be lost over time to the groundwater table, bodies of water such as streams, rivers, and lakes, or the atmosphere. The water cycle, or the hydrologic cycle, describes the continuous movement of water on, above, and below the surface of the earth. Since it is truly a cycle, there is no beginning or end. At any given moment, soil water content is in equilibrium, determined by four main factors acting upon it: gravity, pulling soil water down to the water table; surface evaporation; transpiration from plants; and the soil water potential. The key to understanding the movement of water in soil is the concept of water potential. Let's consider a molecule of water. It is a dipole molecule with one side being positively charged and the other being negatively charged. Water molecules attract each other to create a cohesive force among them. In the soil, additional forces affect the water molecule, and the energy from these forces is called the water potential. A water molecule will move from one place to another if there is a force pushing or pulling at it, and if there are no physical barriers to its movement. This works throughout the water cycle. In the soil, tensile forces, that is, those related to tension, pull or suck water along a water potential gradient. The tensile forces are expressed as negative pressures using various units such as atmospheres, bars, and megapascals. The more negative numbers indicate greater suction forces. If a field, pot, or landscape becomes saturated with water, that is during irrigation or a soaking rain, water will permeate all pores in the soil. After the irrigation event, the major force to act upon the water will be gravity. Most of the water acted upon by gravity flows downward through well-developed channels in the soil created by the soil structure itself, decaying roots, soil-dwelling animals, worms, insects, and other soil organisms. Seepage from smaller pore spaces also occurs. Water will drain out of the root zone by action of gravity until some tensile forces exerted by the soil equal or offset the gravitational pull. At this moisture content, the soil is said to be at field capacity. At field capacity, water occupies almost all of the micropore spaces, whereas most of the macropores are filled with air. Water is removed from a soil at field capacity by the process of evapotranspiration, a combination of surface evaporation and plant transpiration. The driving force of evapotranspiration is the water potential gradient, which draws water through the plant or from the soil surface to the atmosphere. The slope of the gradient is determined by a number of environmental factors, including the radiant energy level, the ambient temperature, the atmospheric vapor pressure, that is the relative humidity, and wind speed. On a typical summer day, a healthy plant growing in soil at field capacity will most likely be transpiring rapidly. Water will be drawn from the soil to the plant's root. Thereafter, it will travel through the vascular system to the leaf surface. Look carefully at the image on the right and note the movement of water. At the leaf surface, water will be vaporized as it escapes to the atmosphere through epidermal openings called stomates or stomata. Plants are only able to utilize capillary water held in soil pore spaces. At first, this water is relatively easy for plants to remove. However, as water moves from soil to the roots or slowly evaporates directly from the soil surface, the soil water potential becomes more negative. The remaining water is increasingly more difficult for plants to remove. The point at which the soil's pull on the remaining water equals the pull of the plants is called the permanent wilting point. The permanent wilting point is a soil characteristic, not a plant characteristic. At the permanent wilting point, most, if not all, of the capillary water will have been extracted by plants. The permanent wilting point varies for different plants and soils, but is usually around negative 1.5 megapascals. The difference between soil moisture levels at field capacity and permanent wilting point is called available water. The amount of available water is highly dependent on soil type. Because clay soils have a greater quantity of pore spaces, they will retain more water at field capacity and at the permanent wilting point than loamy soils or sandy soils. However, there may be as much as twice the available water in a clay soil at field capacity as in lighter textured soils. Now that we've seen the basic relationship between soil, water, and plants, let's consider some larger issues related to water availability for plants in different areas. About 75% of the land area of the world is classed as being semi-arid or arid, receiving less than 50 centimeters or 20 inches of water per year. Crop growth in these areas is often highly dependent upon irrigation. Although irrigation is also practiced in non-arid areas, to offset periodic deficiencies in rainfall. Most agronomic crops in the United States east of the Mississippi are produced under rain-fed conditions. If one looks at the moisture balance for the north-central United States, one sees a surplus of precipitation over evapotranspiration, indicated on the map by regions in shades of green and blue. Thus, more precipitation occurs in this region than can or than is normally lost by evaporation. However, these two processes are out of phase, meaning that while precipitation is relatively constant throughout the year, in this example here for Indianapolis, there is excess evapotranspiration in the spring and summer. Leading to water deficits during the growing season. Although the amount of precipitation and total evapotranspiration paints a picture of the availability of water for growing plants in different regions of the country, the picture is complicated somewhat by the water holding capacity of the soil. We can express available water content in the soil as a depth of water in inches or millimeters in order to compare it with precipitation. Thus, in the region where plant roots are active, there may be about 100 millimeters or 4 inches of water in a typical soil at field capacity. This would correspond to 3 to 4 weeks of evapotranspiration in the summer. This length of time without rain in a Midwestern USA summer is not terribly unusual, and the consequences can be rather deleterious to plant growth. When it rains on dry soil, water will be absorbed as long as the rate of precipitation does not exceed the rate at which rainwater can infiltrate the soil, the infiltration rate. If the rate of precipitation exceeds the ability of the soil to absorb water, then the excess water will run off. When the soil reaches field capacity, all of the precipitation will run off or drain through the soil to the water table and beyond. Thus, a portion of the rainfall is not available to plants. At one time, before land was converted from forests or prairie to agricultural use or for human habitation, water would have accumulated in ponds and puddles or wetlands to be absorbed over time. This is undesirable in most crop situations, as overly wet areas are not suitable for the growth of many plants. In addition, the winter surplus of precipitation, which could help to balance the summer deficit, makes the soil too wet for crop establishment in the spring, so drainage has been installed throughout the Midwest. In fact, tile drainage is essential throughout much of the U.S. Corn Belt to allow for timely planting and to minimize saturated soil condition. So let's summarize some of what we learn about the relationship between soil and water. Water landing on the soil surface can run off or infiltrate through soil pores. Some of the infiltration may drain through the soil to groundwater or out to streams and rivers, or some may evaporate, either directly from the soil surface or through plant transpiration. The amounts of water draining through and retained by soils have long-term effects on soil properties. Water is present in the soil in macropores, in micropores, and bound to hydrophilic groups on the surface of mineral and organic matter. So let's consider overall the key points for this section. And when soil has been fully wetted and allowed to drain under gravity, it is said to be at field capacity. The bound water on soil particles is the last to be released on drying and unavailable to plants. When only bound water remains, the soil is said to be at permanent wilting point. The difference between field capacity and permanent wilting point is plant available water. How about some review questions then for considering the content of this section? How does water move from the soil through the plant and into the atmosphere? Why may a plant wilt when the roots are submerged in water? And what is the soil water potential? What is the function of stomata? What is meant by soil life field capacity and permanent wilting point?